Let us now calculate delta S, the change in entropy for the system, under conditions that are non-reversible. For instance, let us consider the vaporization of water liquid at 35 degrees Celsius and 1 bar. Vaporization of water liquid at 1 bar is only reversible at 100 degrees Celsius. When a phase change occurs in non-reversible conditions, one cannot use the equation delta S equals n delta H standard divided by T. Instead, one must imagine a reversible path between the same initial state as the real process, here water liquid at 35 degrees Celsius and 1 bar, and the same final state of the real process, here water vapor at 35 degrees Celsius and 1 bar. To do such calculation, we use the cycle method and write first the actual process, which we call star, and which consists in the transformation of n moles of water liquid at 35 degrees Celsius and 1 bar into n moles of water vapor at 35 degrees Celsius and 1 bar. Now we need to imagine a reversible path between initial state and final states. Since we know that the vaporization of liquid water at 1 bar is reversible at the temperature of 100 degrees Celsius, then we use this process as one of the reversible steps of our imaginary path. To complete this reversible path, we need to add two reversible steps. The first step, which we call step 1, consists in a reversible isobaric heating, that is the slow heating at constant pressure from 35 degrees Celsius to 100 degrees Celsius of n moles of water liquid. The other step, which we call step 3, consists in a reversible isobaric cooling from 100 degrees Celsius to 35 degrees Celsius of n moles of water vapor. Let's call step 2 the reversible vaporization of water liquid at 100 degrees Celsius and 1 bar. From the thermodynamic data tables, we can extract values for the standard enthalpy of vaporization and for the molar heat capacity at constant pressure for the liquid and vapor phases. Then we write the change in entropy through the reversible path 1 plus 2 plus 3 as the sum of delta S for step 1 plus delta S for step 2 plus delta S for step 3. In the preceding lecture, we learned that the change in entropy as a result of heating or cooling n moles of a pure substance under isobaric condition is equal to n times CPM times the natural logarithm of the ratio of final temperature to initial temperatures. This is what we use for step 1 and 3. In step 1, we use the molar heat capacity of the water liquid, while in step 3, we use the molar heat capacity of water vapor. Note that the final temperature for step 3 is the initial temperature for step 1 and vice versa. Make sure you express all temperatures in Kelvin. The change in entropy for step 2 was calculated on the preceding slide as n moles times delta vaporization H standard divided by 373.15 Kelvin. So we obtain delta S as 234 joules per Kelvin. Please note first that this value differs from the value calculated at 100 degrees Celsius. Second, note that delta S for step 1 is positive because step 1 is the heating of water liquid, while delta S of step 3 is negative because step 3 is a cooling of water vapor. At this point, it is also important to realize that we cannot say anything about the spontaneity of water vaporization at 35 degrees Celsius because all we have done is calculate delta S for the system. We still need to calculate delta S for the surroundings and delta S for the universe, and finally check the sign of the latter quantity. The second step in our calculations is to determine the value of delta S as a result of a phase change for the surroundings. The equation we use for the entropy change in the surrounding is always delta S surroundings equal to Q surroundings divided by T surroundings, equal to minus Q for the system during the actual process divided by T surroundings. Again, we will use the vaporization of n moles of water at 35 degrees Celsius and 1 bar as an example. Delta S surroundings is equal to minus the heat of vaporization of water at 35 degrees Celsius divided by 35 degrees Celsius expressed in Kelvin, that is 308.15 Kelvin. Vaporization occurs at constant pressure, so the heat of vaporization at 35 degrees Celsius is also equal to the change in enthalpy associated with the vaporization process at 35 degrees Celsius. Thermodynamic data on vaporization is typically tabulated at the normal or standard boiling point of a substance, or at 298.15 Kelvin. So we need to relate the vaporization enthalpy at 35 degrees Celsius to a given vaporization enthalpy, for instance, at 100 degrees Celsius. To do so, we could use the Kirchhoff equation, or better, the cycle method, which we just used on the preceding slide. With the cycle method, we first write the actual process, that is, vaporization of water at 1 bar and 35 degrees Celsius. We call that process star. Then, below that, we write the same process under conditions for which we know the value of delta H standard. Here, we chose to write the vaporization of water at 100 degrees Celsius. Then we complete the cycle by drawing the arrows for step 1, corresponding to the isobaric heating from 35 degrees Celsius to 100 degrees Celsius of water liquid, and step 3, corresponding to the isobaric cooling from 100 degrees Celsius to 35 degrees Celsius of water vapor. Step 2 corresponds to the phase change at 100 degrees Celsius. The total change in enthalpy for the imaginary path 1 plus 2 plus 3 is the sum of the enthalpy changes delta H for step 1 plus delta H for step 2 plus delta H for step 3. If we carry out these calculations for 1 mole of water liquid, we write delta H for 1 equals CPM for water liquid times 373.15 Kelvin, the final temperature of step 1, minus 308.15 Kelvin, the initial temperature of step 1, equals 4,893.85 joules per mole. Delta H for step 2 is equal to 40,700 joules per mole at 100 degrees Celsius. Delta H for step 3 is equal to CPM for water vapor times 308.15 Kelvin, the final temperature of step 3, minus 373.15 Kelvin, the initial temperature of step 3, equal minus 2,182.7 joules per mole. So we obtain delta H vaporization at 35 degrees Celsius equal 4,893.85 joules per mole plus 40,700 joules per mole minus 2,182.7 joules per mole equal 43,411.15 joules per mole. And for 2 moles of water, delta S surroundings equals minus 2 moles times 43,411.15 joules per mole, divided by 308.15 Kelvin, equal to minus 281.75 joules per Kelvin. We now have all we need to discuss the calculation of delta S universe for non-reversible phase changes. Over the last 2 slides, we have considered the vaporization of water at 35 degrees Celsius. We found that delta S equals 234.11 joules per Kelvin for the system. This positive entropy change is consistent with the fact that vaporization is always associated with an increase in entropy or a disordering for the water molecules as they move from the liquid phase to the vapor phase. We also calculated the change in entropy for the surroundings to be equal to minus 281.75 joules per Kelvin. This negative value indicates a decrease in entropy or an ordering of the surroundings as they lose heat to the system. That is, of course, necessary for the vaporization, an endothermic process. Finally, adding delta S for the system and delta S for the surrounding yields a value of delta S universe equal to minus 48 joules per Kelvin. A negative value of delta S universe allows us to conclude that vaporization of water is not spontaneous at 35 degrees Celsius and 1 bar. Indeed, under these conditions, the liquid phase of water is stable, not the vapor phase. Had we done similar calculations at temperatures above 100 degrees Celsius, we would have obtained similar sign for delta S and delta S surroundings, but the magnitude of delta S would have been greater than that of delta S surroundings, leading to a positive delta S universe and a spontaneous process of vaporization.